So I've been working pretty much my entire career on artificial intelligence and trying to progress the state of the art in artificial intelligence. But I always had the aim to build it as a tool to accelerate scientific discovery. And obviously AlphaFold and protein folding was the first big challenge that we applied it to.
AlphaFold is a deep learning system, a type of AI system which predicts something called protein structures that biologists do to understand what goes on in the cell and what goes wrong, for example, when you have a disease.
Proteins are the workhorses of biology, and pretty much every function in your body is supported by a protein. But what a protein does in your body is determined by its 3D structure. And so the protein folding problem articulates this idea of, can you predict what the 3D structure will be just from the amino acid sequence? And that, in essence, is what we build the program AlphaFold to solve.
Since we have so many proteins, since we have 20,000 protein coding genes, there's this enormous set of problems that we need to solve to get this whole picture, really to get a kind of parts list of the cell so that we can do more science and better science on top of it.
So when we completed AlphaFold, we actually open sourced the code, and we folded all 200 million proteins pretty much known to science, and made it freely available and accessible to any researcher in the world for any purpose.
So I remember getting a mysterious email from Janet saying she'd like to have a call with no details. And a call with no details is either very good or very bad. So I was thrilled that it was about the Gairdner.
Canada itself created a lot of the new AI booms. A lot of the researchers responsible for that were based in Canada and still are. So yeah, it's sort of quite poignant, I think, that it's a Canadian award for what essentially is applying AI to a grand challenge in biology.
This evening to this Gairdner Science Week public lecture, A New Era in Artificial Intelligence, Envisioning the Future of Health and Science with Demis Hassabis. I'd like to thank our partners, the Public Policy Forum, and all our sponsors for all the events of Science Week, including this lecture. Now, the Gairdner Foundation, as you just heard, gives out awards for amazing science, and the amazing science that was performed by Hassabis and Jumper in determining an algorithm that would allow you to work out the structures of every protein in your body, AlphaFold. And that is essentially what they were given the award for. And they are, both of them, here in Canada this week, along with other Gairdner laureates, to travel across the country and talk about their science to high school students, to the public, and to universities. So the Gairdner Awards really are a way of recognizing the best science in the world and bringing that science to Canada. So I'm just going to briefly introduce Demis Hassabis, because I think many of you have heard of him and know his amazing contributions. He's the founder and CEO of DeepMind, which is now part of Alphabet and is Google DeepMind. He leads Google's AI innovation efforts. And from its foundation in 2010, DeepMind has been at the forefront of AI, producing breakthroughs such as AlphaGo, the first program to beat the world champion at the complex game of Go, and then followed on by AlphaFold. Demis himself, he's a super achiever, what can I say? A chess master at a very young age, a video game developer, then a neuroscientist, and then a leader in AI and an AI entrepreneur at the forefront of AI today. His work's been cited over 100,000 times. He's featured in Science Top 10 Breakthroughs of the Year on 4 separate occasions, Fellow of the Royal Society of London, the Royal Academy of Engineering, and just last month, he featured in Time magazine's top 100 of the most influential people in AI. And so we're going to hear from Demis. And after Demis's talk, we're going to have a moderated discussion moderated by Shingai Manjengwa, who's here tonight as our moderator, who is the head of AI education at Chain Machine Learning and originally the founder of Fireside Analytics. At Chain Machine Learning, she works with clients on AI education,
Thanks, Janet, for the very kind introduction. And it's a real honor to be here this week for the Gairdner and, of course, to receive the Gairdner Award. I'm going to talk about AlphaFold, of course, and the impact that AlphaFold has made. But also, I wanted to just give you a brief overview of the work that led up to AlphaFold and where we see things going from here in applying AI to accelerate scientific discovery in biology and across the sciences. So is there's a slide up? Back in 2013, 2014, where we built our first, I would say, powerful kind of learning system that proved that these types of learning systems that learn from first principles rather than being programmed with solutions, but learned the solutions for themselves, could actually scale up to something interesting and challenging that even humans would find challenging. For example, playing games. And we started with games because they're a very convenient testing ground to test your algorithmic ideas. And games and AI have had a long and storied history together. In the kind of founders of the AI field, people like Alan Turing and Claude Shannon, they all thought about especially chess programs and applying AI to games as a proof of concept that the AI systems were actually capable of doing useful things. So we actually started with the simplest of video games, Atari games from the 1970s, and here we're showing a picture of Space Invaders. And the system that we built called DQN had to learn from first principles what to do in the game. So all it got as the inputs were the raw pixels on the screen, and it was told to maximize the score. But it wasn't given any of the rules, and it had no idea how to score or what it was controlling even, or even the structure of the screen, what was on the screen. It had to learn all of that directly from experience. So DQN ended up mastering all the Atari games. You know, there's sort of dozens and dozens of challenging games, very famous, iconic games like Space Invaders. And DQN, the same system out of the box, was able to play more than 50 of these games to a very, very high level. Building on that, then, we took our work in games to a sort of pinnacle with AlphaGo, which was our system to master the game of Go through a process of self-learning. And Go, for those of you who don't know, it's an amazing game. I really encourage you to try it if you haven't played it. It's over 3,000 years old. It's the oldest game humanity has invented. It's still a huge number of players play it today, over 40 million active players. It kind of occupies the echelon that chess does in the West in Asia. So in Korea, in Japan, in China, Go is the kind of pinnacle of the games that they play. But the complexity of Go is enormous. It's actually far more complex than even chess. And one way to to easily sort of illustrate that is that there are 10 to the power 170 possible positions in Go, which is far more than there are atoms in the universe. So what that means is you cannot possibly brute force your way to like examining every possibility so that you pick the right move to win the game. It would take, you know, longer than the age of the universe to calculate that. So you have to do something much cleverer. And that's what we did with AlphaGo, is that we basically built a system that was able to, and through playing against itself millions of times, was able to build up an idea, a picture of the game of Go, a model of the game, so that it was able to predict from any position who was likely to win and by what percentage. And then we can use those models to simplify the amount of searching that you have to do and the number of positions you have to assess before picking the right plan. So that makes this whole game of Go kind of tractable and possible for computers to actually play well. And then we famously had a $1 million challenge match against the legendary South Korean world champion Lee Sedol, who's a kind of living legend of the game, one of the strongest players of all time. And it was a huge match, as you know. We'll never forget. It's kind of like all of us that were there as a kind of once-in-a-lifetime event. And over 200 million people around the world watched the match live. And it was made into an award-winning documentary, which is available on YouTube if you're interested in the behind-the-scenes of what happened when we were there in Korea. And AlphaGo amazingly kind of won the match 4-1, which was obviously fantastic. But it wasn't just the fact that AlphaGo won the match. More importantly was the fact that actually it played many creative moves and came up with new creative strategies that no one had ever seen before, even though we've played Go for 3,000 years and professionally for hundreds of years. So it's kind of amazing that AlphaGo was able to come up with completely new ideas that hadn't been thought of before. And the most famous of these was, you can see on the right-hand side there, move 37, the 37th move in game 2 of the 5-game match. And that's this game and this move has now gone down in sort of Go legend, and all the Go books have been rewritten with these ideas in them, because you'll see that it's marked in red here on the board on the right. That's the position on move 37. It's very early in the game. And the key thing to note about the stone that's marked in red on the right-hand side there is that it's on the 5th line. So on Go, you play 19 by 19 board. And generally, you play on the edges in the early part of the game. You don't play towards the center. And if you're a professional player, you would never play on the 5th line this early on in the game. And in fact, the commentators, the professional commentators who were commentating live, literally nearly fell off their chair when they saw this move. And they actually, some of them commentated that they thought that the computer operator had misclicked to the wrong square because it was so unthinkable. And then it turns out that 100 moves later, the fighting from the bottom left corner of the board spilled out into the middle, and then that was resolved precisely where this move 37 stone had been placed. So it was almost as if AlphaGo presciently sort of predicted ahead of time that was going to be the decisive place to put a piece, so that it decided that battle and that decided the whole game. So it's it's definitely, I would say, an example of an AI system being creative. But it's interesting, to kind of consider what that means, because creativity, obviously, there are quite a lot of definitions of what creativity is. But let's, for a simplicity, just take a simple operational definition of creating something. Creativity is sort of coming up with something new that has never been seen before. Then I think you could kind of say there are 3 levels of creativity, and AI systems are currently able to do the first 2, but not the last one. So the lowest level of creativity I would call interpolation. So there you can think of an easy example would be like if I showed an AI system 1 million pictures of different cats, and then I told it to come up with a new picture of a cat that's not in any of those training images. It could just do an average of all the cats it's seen and kind of create and output that as the prototype cat. And that cat would be in some ways original, because that cat picture, because it doesn't exist in any of the examples. But obviously that's a very simple form of creativity. Then the next step would be extrapolation, and I think AlphaGo exhibits this, where you actually extrapolate from the things you've seen or the things that you've experienced, and you extrapolate something new that is out of distribution, that's not in the distribution of what you saw before. And I think move 37 is a good example of that. Like, no human player in the history of Go would have played that move. But AlphaGo came up with that, and later it turned out to be a really great move. But then the final step is, I call invention, or you can think of it as out-of-the-box thinking. And that is, if we were to sort of analogize to this situation, then that would be like not coming up with a new Go strategy or a new strategy for chess or some new game, but you actually invent Go. Not just come up with a new Go strategy, but invent the game of Go. And so far, our systems, of course, can't do that. No AI systems are able to do that, partly because we don't necessarily know how to specify that in the right way to an AI system, but they don't have the ability to invent to that level, which, of course, us as humans are able to do. And, of course, we invented Go. So that's still to be determined, and no one knows how to do that yet, although I don't think it's impossible for an AI system to do it. But, of course, we have a lot of work to go if we're wanting to reach that level of creativity. So then we've been lucky, and we continued this sort of kind of games work, and we took AlphaGo, and we built a system called AlphaZero, which was able to play any two-player game, not just Go, but chess, with backgammon, drafts, any two-player perfect information game. And then we finally finished off with AlphaStar, which was a system to play the real-time strategy game StarCraft, which is the hardest sort of computer strategy game, and is more difficult than board games because you only see part of the board. It's partially observable, it's called. So you have to actually go and find the information about what your opponent is doing. It isn't just presented to you. So it's kind of additionally challenging. Now, this was our work in games, but games was obviously just a means to an end. It was a lot of fun, and I could work on games my whole life, but it was just to test out these algorithms, and the idea was to build general-purpose algorithms, not just to play these games, but that would be transferable to other domains, to real-world problems. And the exciting thing that's happened in the last few years is that I think finally we're at that point now where we have powerful and sophisticated enough algorithms, learning algorithms, that we can apply it to very challenging real-world problems. And for me, my passion has always been, and the reason I worked on AI my whole life, is applying AI to scientific discovery itself as a kind of ultimate tool to help with science. And what we look for, and what I look for in picking a problem to tackle is, kind of three properties of that scientific problem. We really love massive combinatorial search spaces, a bit like the one I showed you in Go, where this hugely dense, complicated search space, and you can't do it by brute force methods. So you have to use a learning system to learn a model of the environment and the situation. Secondly, you need to have a clear objective function or kind of metric that you are trying to optimize against. So obviously in a game, that's pretty simple. It's like maximizing the score or winning the game. But a lot of scientific problems can also be cast in this way, like minimizing the amount of free energy in a system, for example. And then thirdly, what we look for is you need to have quite a lot of data to train these systems and for these systems to learn. And that can be real-world data, but it can also be data that it's self-generated or generated synthetically from a simulator. And ideally, you have a problem, you pick a problem that has both quite a lot of real data and also an accurate and efficient simulator. So that then brings me to AlphaFold and the protein folding problem. So that was always very high up on my list. I have a list of sort of big scientific challenges that I would like to tackle with AI, and sort of collected it over the last 20, 30 years. And protein folding was always at the top of that list. And for those that don't know what the protein folding problem is, I'll just quickly explain it. Proteins are essential to all life. Every function in your body depends pretty much on proteins. And what's important about protein is its 3D structure. So you can see on the left-hand side a protein specified by what's called its amino acid sequence, which you can think of as a bit like the genetic sequence for the protein. And then in the body, and in nature, it folds up into a 3D structure, like a scrunched up ball. And the 3D structure is it tells you a lot about the function that protein carries out in nature. So it's very important to understand, to have that structure. But the problem is that determining that structure experimentally often takes years and years of painstaking work on very expensive and complicated equipment. So the idea of protein folding problem is, and it was proposed first by Christian Anfinsen in his Nobel lecture almost exactly 50 years ago now in 1972, is he proposed this conjecture that you should be able to tell the 3D structure of a protein directly from this one-dimensional genetic sequence, the amino acid sequence. And it basically sparked off a 50-year grand challenge in biology. It's a bit like the equivalent of Fermat's last theorem in maths, where, you know, just sort of this throwaway comment of like, it should be possible, and then sends, you know, hundreds of great scientists for 50 years trying to actually unravel that and make that come true. So it's been, you know, a dream, I would say, of the biology field to have a solution to this problem, and it would speed up many areas of research, including drug discovery and disease understanding, if we could, if we knew the 3D structure of all the proteins in nature and in the human body. So why is this such a hard problem? You know, and that's the question really, is can the protein structure prediction problem be solved purely computationally? And it's a hard problem because Leventhal, one of the contemporaries of Anfinsen, he articulated, it's now known as Leventhal's paradox, as he calculated that there are around potentially 10 to the 300, so that's 1 with 300 zeros, possible shapes that an average protein can take. So it's absolutely astronomical, far bigger than even the number of positions in Go. But of course, in nature, somehow, and in our bodies, somehow these proteins fold up in sometimes in like milliseconds, spontaneously in milliseconds. So physics and nature somehow solves this protein folding problem. But, you know, on the face of it, it looks intractable given the number of possibilities. So that's the paradox. And then the other reason we picked this problem is that there's this amazing competition called CASP, which runs every 2 years, and it's sort of known as the Olympics of protein folding, right? So all the best teams around the world enter it every 2 years, and it's a phenomenally well-run competition. It's been running for nearly 30 years by an amazing person called John Molt, who's dedicated a lot of his life to running this competition. And the cool thing about it is it's a kind of double-blind test. So experimentalists who've just discovered a new protein structure through one of their experimental methods, just before they publish it, they actually enter it into this competition, and then that amino acid sequence is given to the participants, and you have to send back a prediction of the structure before the publication comes out. And then obviously when the publication comes out, you know, a few weeks after that, you can, the competition organizers can compare your prediction with the ground truth, with the actual experimental data. So it's a beautifully run competition. And that makes it very attractive to kind of try and improve against. And so this here is a chart of the 10 years prior to us entering with AlphaFold 1, so from 2006 to 2016, of the winning team and the score that they got, the accuracy score they got on these test proteins. And in order to solve this problem, what we were told by, you know, biologist friends of mine and the field is that you have to get to accuracy, predict the structure of the protein to the accuracy of within the width of an atom. So it's 1 angstrom. So less error than the width of an atom. And the reason that's so important is that's the accuracy you need in order for experimental biologists to be able to actually use it for their experiments. So that's obviously very challenging. And that width of an atom, that 1 angstrom error, translates to about 90 on this axis, the y-axis here, 90 GDT it's called, which is the score that they give to your predictions. And you can see here all the winning teams on the hardest category were topping out around 40 GDT, so miles off the accuracy that one would need. So we entered AlphaFold 1 in 2018, and that won the competition by a large margin, but it also improved this sort of winning score by nearly 50%. So that was pretty astounding for the field. And the reason it improved so much is for the first time ever, AlphaFold 1 introduced cutting-edge machine learning, some of the techniques I showed you earlier and we did for things like AlphaGo. We translated them over into this problem, and no one had ever done that before, actually applied machine learning as the core part of the system. But we weren't satisfied with that, just that. Of course, we wanted to get to this 90 level, and we did that with AlphaFold 2, where we re-architected, we took the learnings from AlphaFold 1, and then a couple of years later entered Cas14 and won the competition again, but this time we did reach atomic accuracy across all the test proteins, and that led the organizers to declare the problem essentially solved. So this is what it looks like, and protein's extremely beautiful, and I've obviously spent 5 years now looking at and learning about these incredible systems, and proteins are almost like little bio-nano machines, and it's just amazing to me how they all work together in this intricate kind of dance, and perform all these functions that keep us alive and basically gives birth to life. And what you can see on the right-hand side here is AlphaFold incrementally building out, and this is one of the processes of AlphaFold. It sort of feeds back its previous prediction, and it makes a better prediction. And you can see it over different amounts of times. After around 150, 160 times, it ends up on the final structure, which you can see on the right-hand side. And then on the left, you can see the final predictor structure in green, in blue, overlaid with the real structure in green. And you can see how close the prediction is to the actual structure of this incredibly complex protein. So we then went on to release this to the world so that the scientific community could make use of it. We collaborated with the wonderful European Bioinformatics Institute, just up the road from where we're based in London. They're in Cambridge, and they build all of the current main biology tools that biology researchers use, all the big databases. So we thought they would be the best people to take this data and take our algorithms and host that for the scientific community. So we published the methods, we open source the code, and all the predictions for anybody to use, any researcher, any pharma company to make use of. And then so we started off by folding all 20,000 proteins in the human body, so the human proteome, that's called. It's a bit like the human genome, but in protein space. And then we calculated, not only is AlphaFold extremely accurate, it's also very fast. So we realized that if we used a year of a lot of computers, but spent a year folding, we could fold every protein known to science, every protein in nature. So all 200 million proteins that we know of in nature. So we folded all of those over the courses of a year, all the important research animals, crops, all sorts of very, very important organisms, and we put them up on the database for anyone to use, free and unrestricted. Of course, I'll talk a little bit about what the community's been using it for, but best before we did that, safety and ethics has always been a key part of what we do at DeepMind and Google DeepMind now. And it's no different here. We consulted with over 30 experts in biosecurity, obviously biology research, and also in human rights as to what we were going to release and make sure that it was beneficial, the benefits outweighed the risks, which they all unanimously came back and agreed with. Oh, so one thing I should mention here is that 200 million proteins, it usually takes, often takes, can take a PhD student, a grad student, their entire PhD to find the structure of one protein experimentally. So, if you think a PhD can take an average of 5 years, then 200 million structures would have taken 1 billion years of PhD time. So it's kind of amazing, really, to think of it in that way. So what has it been used for? It's been amazing. We've been kind of amazed by what the scientific community has done with all of this and the diversity of things they've applied AlphaFold to, from designing plastic-eating enzymes to important structural biology, like determining the nuclear pore complex, one of the biggest proteins in the body, to looking at designing new vaccines. We're especially proud of the neglected disease work that one of the early adopters of AlphaFold was the Drugs for Neglected Disease Institute, part of the WHO. And they work on things like leishmaniasis and Zika virus and viruses that and diseases that affect the poorer parts of the world and often don't have a lot of pharma working on that and pharma companies working on those things. And here we're able to give these NGOs directly the protein structures for the bacteria and the viruses that they were interested to combat. Another example, just in numbers of the impact of AlphaFold, is over 1 million researchers have used now the database in AlphaFold in pretty much every country in the world, and it's been cited over 15,000 times now in just over nearly 3 years now. So it's been, the impact's been incredible to see. And I'll just end with a few thoughts about where this is all going. So I like to use this phrase, science at digital speed. And I think we're going to see more of this soon. And I think AlphaFold is maybe the first example of that. And I mean it in two ways for AlphaFold. So one, of course, is that it's able to find the structure of a protein incredibly quickly. So for an average protein, it only takes a few seconds. So that's obviously amazingly fast compared to experimental methods. But also, you can disseminate that solution extremely quickly with technological means, putting on a database, hosting on a database for everyone to use. And it's as simple, for wherever you're accessing it from, whichever research you are from, whichever country in the world, it's just a keyword search away and you get that 3D structure and all the details about it. So that's why we think it's been adopted so quickly and being used by so many people so quickly, because it is a sort of digital solution. So I think now, if we look forward, this is hopefully, I think, heralding and maybe a new era of what I like to call digital biology, where you can think of biology as a fundamental level as an information processing system that resists the second law of thermodynamics. It kind of tries to keep its structure together. Of course, it's an enormously complex and emergent information system, but it might actually turn out to be the perfect type of regime for AI to be applied to. So AI is very good at picking up these kind of weak signals and trying to make sense of them. So I hope that when we look back in maybe 10 years' time, AlphaFold won't just be an isolated success story, but actually perhaps heralds a new era of digital biology solutions. And we've actually ourselves spun out a new company called Isomorphic Labs to try and take this a lot further into biochemistry and chemistry to actually reimagine the whole drug discovery process from first principles with AI. And we would like to speed up the discovery of new drugs by an order of magnitude, taking months instead of what it now takes is years. So then if we just step back and think about putting all these things together, then what I think we've done with our systems from AlphaGo to AlphaFold is build these models that allow you to search these enormous search spaces to find an optimal solution. So this needle in a haystack, whether that's the correct protein fold or the best move in a go position, you're searching through this enormous space to find that optimal solution. And so in order for you to be able to do that, for the system to be able to do that, it needs to create this really good model of the environment, obviously based on data or simulation. And then it uses search on top of that. It uses that model to guide the search to only look at the things that are most likely. And although, you might think that's kind of restricted way to look at things, but actually it turns out many, many problems, both in industry and in science, can be solved in this way if you kind of couch it in these terms. And so here's just that example, finding the best go move. You can think of a tree of all possible moves, and the pink line is like what AlphaGo has found to be the best continuation. But now you could just replace those nodes. Instead of go positions, they could be chemical compounds, on the way to designing a drug that minimizes things like side effects and toxicity. So very much the same, I see a sort of direct analogy, and the same kind of processes could be used. And we're not just applying this to biology, we're applying it to many other fields, quantum chemistry, pure mathematics, even things like fusion, plasma containment infusion reactors, and genetic mutations. And we've had a lot of success in the last couple of years applying these similar types of techniques to these widely varying fields. So I'll just end then by talking a little bit about, I've talked about all the exciting opportunities and the advances we're making, but of course we need to do this, we need to sort of pioneer in a responsible way. And I think AI has an incredible potential to help with humanity's greatest challenges, things like disease and medicine. But of course, we have to use it responsibly and safely for the benefit of everyone. And that's always been our priority at DeepMind and at Google. And we have our Google AI principles of how we will deploy AI. And we continue to try and be thought leaders in this space of AI strategy, risks, and ethics and safety. In fact, there's a big summit next week in the UK with many heads of state coming that will be prominently talking there and talking about these types of issues. And so I'll just end by then saying, I think that we should use the scientific method as we're approaching this very pivotal moment in human history and sort of not do the typical Silicon Valley thing of moving fast and breaking things and then fixing them afterwards. I think this is too important a technology to work like that, and something as transformative as AGI requires exceptional care. And our mantra at Google DeepMind is to be bold and responsible. So bold with the opportunities, but responsible in mitigating the risks. And if we achieve eventually AGI in the years to come, I think we can consider it to be maybe the ultimate general purpose tool to help us understand the universe around us. Thanks for listening.
Is a lofty topic, so my job is to make our speaker feel comfortable. So I'm going to pick a topic he's comfortable with, chess. And let's add some pressure here. You're down to the wire. Which piece are you going to choose? A bishop or a knight?
Well, look, I think that's the beauty of chess, is the bishop and knight have such different capabilities, but they're worth the same amount of points. They're 3 points each, but I would have to say the knight is my favorite piece. So
okay,
I'll take that.
All right, so
we've
got the knight under pressure. So does that mean it's more your game of chess? Is it more a closed game? Do you want to keep things tight?
Yeah. Well, when I used to play chess a lot when I was young, I used to prefer positional chess games rather than tactical ones. So the knight's better for that.
Fantastic. Well, when one is a chess prodigy, you're obviously not new to receiving awards. But this is a different kind of award for science. What does this one mean to you?
Yeah, it means a huge lot. It means an amazing amount to both myself and also especially the team, the AlphaFold team, because it's an amazing award, an amazing accolade, and I think it just brings home and recognizes the impact that AlphaFold has had and that we dreamed about having when we've been working very hard on the project for more than 5 years. So it's great to get that award from the scientific community and medical community, because I think it means that it's had a great impact and people find it useful.
Do you miss the days when no one was talking about artificial intelligence?
I do, actually. I much prefer just quietly beavering away on the research, and the hype today is a little bit out of control, I would say. I mean, it's phenomenal technology, and of course I've believed in it for decades now, and it's fantastic to see it working to the level it is. But I would really, it would be better if it was maybe more considered how we were advancing the frontier rather than what it seems like at the moment, which is more like the Wild West. So, but, I guess that's what happens when it becomes obvious something is ready to come out of the lab and be commercial and things like that. Then, of course, you're going to get a lot of money and attention and other things coming into the field beyond the scientists that were originally already there just because we were passionate about it.
Well, you have our attention now, and so maybe just to make it more concrete, for the rational economic man walking around on Bloor Street just outside this theater, what is your discovery, what does AlphaFold mean for them?
I think, I alluded to it a little bit in the talk of I hope, it's advanced a lot of fundamental biology, so it's definitely helping scientists understand our bodies and disease much better, but I think in practical terms, I really hope it will help accelerate drug discovery and cures for terrible diseases. So, and that's always one of the things, maybe the main thing I wanted to apply AI to one day when I was, working on it as a kid even. That's what one of the most major things that I thought AI would be of use for.
Fantastic. And when do you think we'll start to see those first waves of drugs being discovered?
Well, actually, so when I talk to friends and acquaintances in big pharma, I think all of them, every department in the big drug companies are using it. So I've been told it has already accelerated many drug discovery programs. Some startups have been using it. I think there's a couple of drugs in clinical trials already that have been at least partially helped with AlphaFold. So I think it's just the beginning. Of course, all of that stuff takes time, and it's only been a few years, but I think in the next 5+ years, I think we'll start seeing a lot of drugs in the clinic that were helped by AI, and hopefully some of the work we're doing at Isomorphic Labs will be part of that.
So we've seen medical discoveries before that have changed the world, but they don't always get to everyone. So how do you feel your technology may be used to advance inequality, or is it going to be one of those things that may also advance inequality?
Well, I think if you look at AlphaFold specifically, that's why we put it out there free for everyone on these massive databases that anyone can access. So I'm particularly pleased about the 190 countries part. I mean, I think it's pretty much every country in the world. Researchers have accessed and utilized the structures. And it's also good, I think, because it means even in countries that don't have well-resourced labs, they can still make use of the structures that we found and advance whatever it is that they're interested in. I think in general, if you're asking about the question of AI in general, which you might be, then of course, I think these advances are coming very rapidly. I think that will bring in a lot more productivity and resources into society, but then it's down to us as a society to make sure that those advantages and those kind of benefits are distributed widely to everyone. So I think part one is like creating more of those resources, and I think AI can help with that, but then that doesn't solve the part of making sure that gets distributed fairly and widely. So I think we have to sort of work on both those aspects.
It's a follow-up question, and perhaps it's oddly self-serving, and it's about bias. I've been working with large language models, and we're seeing a lot of bias and hallucination, and I check a lot of boxes, black, female, from Africa. So if bias exists, then a lot of the times I might be affected by that. In your research and in the work you've been doing, did you come across any bias? Did you do any bias testing? Does it exist at that level?
Yeah, I mean, so we do a lot of that work on our more general systems, so testing for bias and fairness, and we've done a lot of leading research on that and making sure the outputs of these systems are fair. But actually with AlphaFold, obviously it's a pure scientific problem. So, proteins are out there in nature, and they're kind of fundamental building blocks of biology. So in that particular case, the things we were more worried about was biosecurity and safety of things like, for example, viral proteins, proteins that are parts of viruses. So we actually removed some of those things for safety reasons. So it was more looking at that kind of risk in that particular case of AlphaFold. But of course, for more general systems like large language models, there's a huge variety of more societal things that we need to look out for in terms of the outputs that they're doing. And we have many different tests and whole departments that look at for these types of things. And we've still got a lot of work to do because it's hard to prove mathematically that those things aren't in there, right? You have to just do massive empirical tests for those things. But it would be better if we could have robust mathematical proofs of fairness and things like that. So hopefully that will be coming in the next few years.
I believe it will. And certainly the focus from your organization, I love that, firstly making the data available to 190 countries also means that different groups working on these problems will bring their contexts and their communities into the discussion. Have you seen any interesting work coming?
Oh yeah, for sure. I mean, that's what I was mentioning about the DNDI, and they were we gave it to them first, actually almost a year before we even published it, because we wanted to accelerate their work in things like leishmaniasis and Zika and other viruses that they and diseases that they work on. And so Changas disease is another one. So obviously that's what those NGOs are looking at in the parts of the world they work in, and they just were amazed by what we could kind of accelerate their work straight to drug discovery, because they didn't have to worry about crystallizing the proteins or doing all of that painstaking work. They could just take the AlphaFold structures and actually get straight to the drug discovery part. So I'm really hopeful. I mean, of course, that part it's very hard too, which I'm also hoping to help with AI downstream, but that's more in the chemistry space, you know, designing small molecules and chemical compounds that will bind to the right parts of the protein to, you know, if it was a virus, to kind of block its function. But it, you know, accelerates them forward many, many years, hopefully.
So this advancement definitely has workforce implications, and you mentioned the PhDs and how many PhDs it would take to get to the point that you're at now. And I know we have PhDs in the room, and it's actually one of the questions that came up through Slido. Remember, if you want your questions, if you want me to see your question, please post it on Slido. One of the questions was, well, what's your message for PhD students, right? Because the formal education systems may not have caught up to what you're doing. So what would you say to the PhD students who are in programs now? Yeah,
well, I'm actually, when I went to, when we first released AlphaFold, we did a lot of talks at some of the big UK universities and labs. And what I was amazed is within a few months, the new PhD students already had adopted AlphaFold and were using it as part of their completely standard part of their workflow. So they didn't even think about it anymore as a new thing, because they'd started their PhD just after AlphaFold had come out, and they just thought, well, of course we have this resource and we'll make use of it. And then, you know, then that frees them up. Instead of doing maybe some of the painstaking crystallography work they would have done, perhaps it frees them up to downstream understand the function of the protein, or maybe design a compound to bind to it, and those kinds of things, and look at the more the dynamics of the situation rather than the static picture of getting the 3D structure. So there's always, it's not like science is solved. There's plenty and plenty of things to do. And I think that's what good technology has always done in the past, is it sort of is a really helpful tool that then frees you up, whether you're a PhD student or a professor, to think of the next level up in the problem stack.
A follow-up question to that, also from Slido, was a doctor in the audience was saying, how should healthcare workers prepare for what's coming down the track based on your work?
Well, that's a lot further down the track, I think, for actually being, you know, in the hands of healthcare workers. Obviously, that's eventually what will happen if the drug discovery process works. So I think the next step is AlphaFold. The structure of protein is only one small part of the whole drug discovery process, right? Just to be clear, it's not solving drug discovery. You need to do many, many other things, but it's an important part of that process. And I do think that other parts of that process, like designing small molecules and chemical compounds that have the right properties, would be amenable to these types of AI systems. And then once they pass clinical trials, hopefully that's when they'll be in the hands of, you know, healthcare professionals.
So we've been very practical in this conversation so far, but many scientists have been talking about AGI, and you spoke a little bit about it. And I actually love your definition, because you just talk about artificial intelligence agents being able to do tasks to a human level. That's the definition that you've provided. What about sentience? It's out there. I have to ask. People want to know, what about sentience?
So, look, so sentience is something I've thought about a lot, but it's of course it's still debated even in philosophical circles, right? So first of all, we don't have a clear definition of sentience, but let's take the kind of usual definition of consciousness. I would say that the systems we have today have no semblance of that, in my opinion. They're just pieces of software. But I think as they become more sophisticated over the next few years, maybe next decade plus, they'll start doing more and more capable things and actually be able to do more and more of the things, cognitive functions and capabilities that we have, perhaps even including creativity, like I mentioned, the invention aspect of creativity. And then they'll get closer. And then I think, and this was always what I thought as a neuroscientist as well, that building an artificial intelligence sort of system or an artifact and then comparing it to what we know about the human mind would probably be the best sort of controlled experiment to understand what is special about our own minds. You know, maybe invention, dreaming, emotions, consciousness would be another one on that list. All of these sort of mysteries of the mind. You know, I'd love to know how that all works, and maybe building an AI construct, whether it has it or doesn't have it, it would be useful either way to kind of compare. It's like, oh, so it turns out you can have systems that are capable and maybe intelligent even, but do not feel conscious in the way another person does to us. So that I could easily believe would be the end result.
So another question that came through Slido was around diseases of the mind. And you know, there's on the one side, we have the work that you've done with AlphaFold, but you're also someone who studied neuroscience extensively. Do you see any kind of bridging of the gap based on that and the studies that you've had in the past?
Yes, so we used it in the early days of AI and the early parts of DeepMind. We used a lot of inspiration from neuroscience, what we knew about the brain. So obviously we only have an incomplete picture and understanding about the brain, but we do know some principles. And I studied specifically the hippocampus, a part of the brain that's responsible for memory. And I also showed that it was useful for imagination as well. Both those things, imagination and memory, are things that we still don't really have in today's systems to a very good degree. And so, you know, you can take principles and architectures and ideas from how the brain solves some of these problems. And then if you're specifically asking about, you know, neurodegenerative diseases, again, I think AlphaFold and the drug discovery approach using AI should be helpful there.
I have a question from the audience. A bioengineering founder would like to know, how can we speed up validation of predicted results in real biological models? How can we better engineer vitro models for this purpose? Any startup ideas?
Good question. I actually do think that would be a great place to do a startup if that's what you're thinking of. So I think the way I think about it is that hopefully we can push more and more of the search into the into computational methods, onto AI and other computational methods, and then you still need to do at the last step, you still need to validate those predictions in the wet lab. So anyone who could speed that part up would be extremely useful, especially for things like clinical trials, which there's still, you know, no way around of doing that, making sure these things are safe to distribute to everyone. You know, half the time is the drug discovery process, and then the other half the time of the 10 years it takes to make a drug is the clinical trials. So if we're able to do those in vitro somehow to a really useful way, and maybe like productionize that somehow, that would be extremely useful.
Well, I'm going to give you this question because it's been upvoted and the people want to know. But I also invite you to let us know if it's something we can share offline after the fact. So it's pulling off of the idea that large language models have been so successful because of the availability of massive natural language data sets. What will be the equivalent data sets in biology? So we're putting you on the spot, but we're also happy to take notes from your team after the fact and share them with the audience.
Sure. Well, look, I mean, anything where there's, I've talked to sort of several really amazing scientists on things like imaging technology, so imaging cells down to like protein resolution and sort of in real time. The problem at the moment is you have to kind of kill the cells in order to image them. What would be amazing is if someone could come up with imaging technology that can actually image live cells to that resolution, and then potentially we could maybe build up a whole model of a virtual cell like that if we got maybe several thousands of hours of videos of how, you know, the insides of a cell are moving around and working. So that would be pretty cool. So some of these friends of mine tell me that's maybe only a few years away, but we'll have to see.
Okay, another one from the group. Have you considered taking on the problem of RNA tertiary structure, given the growing importance of mRNA vaccines and therapeutics?
Yeah, we have. We're actually sort of in the works. We have a kind of, you can think of it like an AlphaFold 3, which is extending, you know, you can think of AlphaFold as solving the static picture of a protein, right? So on its own, in isolation. But of course, in the body, it interacts with other proteins and compounds and ligands, but also RNA and DNA. And we're extending it into AlphaFold to be able to work on RNA as well. And the early results we have look pretty promising. So watch the space, but hopefully in the next year or so, we'll have something pretty cool to show.
Well, the follow-on is, what is next for you, right? So you've just done this groundbreaking discovery and this incredible work. Retirement? Are you slowing down?
Sadly, no. I don't really have that in my makeup to slow down. But you know, on the science side, on the biology side, it's isomorphic labs and going into drug discovery. On the science side, I think I showed the slide of quantum chemistry, mathematics. I'd love to tick off some more things on my list of really amazing problems in science and maths that I think AI could be useful for. And I think we're maybe only a couple of years away from that. And then in general AI, we're working to build, you know, these more and more capable general language model systems and make them kind of multimodal. So there's a lot of work.
And because you're so accomplished, I think the scientists in the room also want to know, how do you have fun?
Well, in the small amounts of time that I have, free time, I do love playing games still, so that's fun. So I do that with my kids, and also I love football and Liverpool Football Club, so that's my relaxation, is watching Liverpool matches.
You will never walk alone.
Exactly. Very, very good.
I'm a Liverpool supporter too.
Oh, you are as well?
Yes,
okay, fantastic. There you go.
Well, we're coming up to time, and I just wanted to get in one last question, which is, this is a bookish audience. What homework do you have for us? Maybe a movie to watch, or a book to read?
Oh, wow, okay. Well, look, I mean, the thing that springs to mind, my favorite book is The Fabric of Reality by David Deutsch, who's this amazing Oxford professor who invented quantum computing. But The Fabric of Reality, I think it's just sort of an investigation into, you know, this around us, like what is reality around us. I think it's an incredible book, and really it's what I want to ultimately try and do with AI, is understand the fabric of reality. And
just a follow-on from that is reality grounded here, or are you looking further up?
Well, that's the big question, isn't it? You know, what here even means. So, yeah, that's definitely probably a topic for offline afterwards.
Okay. Fantastic. Well, that brings us up to time. And I'd just like to make a closing remark. Firstly, thank you so much. I mean, this is
Thanks for having me.
Such a treat for me to sit here. And for all of you, just take a moment. Look around, look at the person next to you. When we start seeing those first waves of drug discovery, or when we start hearing more news coming out of Demis's lab, remember that you heard it from the man himself here, right? Remember this moment and tell your friends when you see it on the news that I know him.
It's very kind.
So congratulations once again. My name is Shingai. It's been an absolute thrill for me to be here and share this time with you. Thank you all for coming, and enjoy the rest of your evening.
Thanks, Shingai.